Well, everybody, welcome to our March meeting. And we already kind of started a little bit. And welcome to all the newcomers. We appreciate it. And we have a new Vice President, Mike Arata, and he's doing a heck of a job. He's got his program committee working hard. They're trying to line up some good programs. So if you got any ideas for programs, or if you know of any speakers, I'm sure he'd appreciate you passing along that information to him.
Yeah, I just want to say, please don't give me all the credit, because Ben and Sarah are very good people to have working on this committee as well, and they're contributing and should get credit for putting in their efforts to help us to get to achieve our goal here. And Joe too. Joe was unable to make the meeting, but we may have to have one more meeting. But I think our small group of 3 or 4 people, I think that's large enough. I think we can work together and continue to hopefully achieve our goal, which is to get some organization and get some good speakers and line them up well in advance. And so far it seems to be coming together. So anyway, so I want to thank the other members of our program committee.
The brief history. The Fort Wayne Astronomical Society, as you can see, was incorporated in 1958. And as far as, from what I've been told, the society was founded as a reaction to Russia's Sputnik launch in 1957. There was a lot of that was done in that time frame to kind of boost the number of people that were interested in space and mathematics, physics, and all that. So there were a lot of organizations that were put together, and there was a real emphasis on STEM type education. So it makes sense that the Fort Wayne Society would have been put together as part of that Sputnik reaction effort. As it says, it's an all-volunteer nonprofit group. We've talked about that a little bit already this evening, the volunteer aspects of it and the nonprofit aspect. But the point that I wanted to bring out was the mission statement, the next point, that the Fort Wayne Astronomy Society's mission is to promote in every way among its members and the general public an interest in and knowledge of astronomy and its allied sciences. And the allied science part is where the spectrograph comes into play. It's one of those allied sciences. Let's see here. I'm having trouble getting my slides to advance. Oop, too many. Sorry about that. So I think most people here tonight are familiar with what the society does, and the addition to that, as someone mentioned, Mike or someone mentioned, that the society has added a spectroscope to its hardware that we've got and its abilities. So provide a spectrograph to investigate what the stars, nebulas, and galaxies are made of is what we have been attempting, Peter, Ben, and myself over the past year or so. So if you haven't been out to the observatory, this is what it looks like, and it has facilities that allow members to set up outside the observatory on these cement pads. There's 5 of them. It doesn't show it in this graphic, but there are electric outlets available, so you can run your telescope without having to bring batteries. The floor itself, as it was mentioned earlier, there are 3 telescopes on the floor. There's a 12-inch LX 200 telescope, the 16-inch RCX 400, which the spectrograph has been mounted on the most recently, and then the original 12.5-inch that's an equatorially mounted telescope. The other 2 are fork-mounted, which has its advantages and disadvantages. Got a rather low fork, so we have a hard time with the spectroscope getting up to the north. The room in the back here is the control room, and over the winter, it's been really handy to have a temperature-controlled environment to be in, so we can operate the telescopes and don't have to spend all of our time out on the floor. Really is pretty cold out. It really is pretty cold when it's 9 degrees out, so it's good to be able to dash in and out and get some warmth. Plus, we have all the control equipment for the spectrograph in the control room, so very handy, much easier on the equipment if it's kind of in the 60 to 70 degree range inside, so summer and winter. So very nice. The roll-off roof part is unique. I understand that that there was input from the Purdue University in Fort Wayne on the design of that, as well as the University of Indiana Architectural Department. So we've got a lot of community involvement. So that's the bit of history. Mainly just wanted to bring up the mission statement and go from there. So let's get right into it. I think this is the right one. Yep. So the goals that we're working towards are to create a resource that's capable of stimulating curiosity about the universe around us. I mean, you can see it in a visual telescope. You could take pictures of it. And with the spectroscope, we're going to be able to take the light apart and see what stars are made of, and other objects like nebulas and galaxies. We want to put together a resource that's capable of supporting academic as well as personal spec projects. And with the discussions with the people at Purdue, I think we're headed in the right direction on that. There were some interested in that. The spectroscope that we have is capable of high resolution spectroscopic studies. So we're going to be able to actually do some scientific work with this. There are groups that do professional and amateur joint projects, and I've been off exploring that, and we've got the right equipment to do that. There are people in the organization that I was having a meeting with just this afternoon that have an LHIRES spectroscope using the same camera sets that we do, and 12 to 14-inch type telescopes. So we're right in the sweet spot. In fact, with the 16, we're actually in pretty good shape. And then how to incorporate this into our public outreach still is something that needs to be talked about. How we might integrate the spectroscope into, Saturday night viewing is something that is on the schedule, but not something I've given a great deal of thought about. But it's there. It's part of our goal set for this coming year. All right, let's see if we can make this go forward. Did we change slides?
Yep.
Oh, good. What is a spectrograph? So for those of you that don't really know what a spectrograph is and does, this was supposed to be just a basic, a very basic description of what a spectroscope does. And the basic concept, as it says here, is that it has components to bend light, to bend the colors that are in light at different angles, so that it separates them, so that you can see these different lines that come from each of the chemicals. Each chemical has a fingerprint of lines that are recognizable, and those chemical element lines are used to go back and identify the chemicals that are generating those. That work started over 100 years ago by a couple of fairly well-known scientists, scientist named Bunsen and another one named Kirchhoff. And as it says here, that they started doing this analysis, this investigation into the lines in about 1859. They didn't have any idea what was creating these lines at that time, but they did see them, and they did notice that they were very distinctive, and they were able to use that to identify all of the elements in the periodic table that existed at that time. And later, around the turn of the century, I think, maybe into the 19-teens, there was an element that was discovered on the sun before it was discovered on Earth. And anybody have a guess what that element might be? What would you think it was? I know you know, Ben. So let PJ answer. Go ahead, PJ. Go ahead.
Hydrogen?
No, that's a good guess. But it was helium. The heli part of helium is from the sun's helios, and so they named it after the sun. And then years later, they were able to find it on the Earth. So one of the early triumphs of spectroscopy is the identification of helium. But it's been used for various chemical analysis in the later part of the 19th century, and so it's actually was well developed at the start of the 20th century. So why are there different colors in the light from the stars? Actually, from any object, there's two parts. There's a continuum radiation, continuum light that comes strictly from heat. So when you heat something up, whether it's the the gas burner on the stove, or if it's a piece of steel in a fire, that turns from red to yellow to to white hot, it all has to do with just the temperature. So that's the continuum radiation, and it basically has all the colors in it. And the temperature that it sits at is the dominant temperature that you see, and that same effect can be used for identifying the temperature of an object, even the temperature of a star. And the other part of light has to do with electrons changing levels. So they change, as they change levels, they emit or absorb specific colors, specific photons that cause the absorption lines that we'll see in the spectras. And it also allows us to have things like lasers of a specific color and your fluorescent lighting. So what makes up a spectroscope? Well, there's about five basic components to it, starting from the right side of the screen here. You have to have something called an observing telescope, and that gathers the light. In the case of the Fort Wayne spectroscope, that observing telescope is the 16-inch telescope. This one's quite a bit smaller that you see here. The next thing is a slit, and the slit is used to shape and create a coherent light source. In order to actually break the light up, you need to have a coherent light source. And that coherent light is passed on to something called a collimator. And the collimator takes this spatially coherent light, but it lines it up into essentially parallel beams as if it were a very long way off, so that they're nicely, the wavelengths, the waves of each light are properly shaped and spaced. The next thing that you need, so the collimator is this telescope-looking device right here, and in fact, these two devices are telescopes. This was a DIY project in the 50s, and they put together this spectroscope based on the fact that they had a couple of these finder telescopes. But the third object that goes in, the third component of the spectroscope is a grating, and a grating or a prism can be used to bend the light, and the grating works by something called diffraction, and the prism works just by the characteristics of light. As it passes through the glass, it bends the light at just different angles based on their wavelength, and that light is reflected by the grating or the prism into this viewing telescope right here. And this is actually used as a telescope in this case. You'll notice for the collimator that the light entered into what would normally be the eyepiece at this end right here, and so it works kind of backwards, putting the light out toward the grating, whereas the telescope in its normal mode is facing the light source. In this case, it's the grating, and it provides the image of the spectra that's created by the interference pattern from the grating. So, in fact, what the telescope is actually focused on isn't the grating; it's focused on the slit back here. So, what you see in the spectra is actually the image of the slit. So if you had a slit, if you had a pinhole, I guess is what I'm trying to say, instead of a slit, you'd actually see a round image or a set of round lines. Well, maybe dots actually, not lines. You'd see dots instead of lines. So you're actually imaging the slit with that. But really, the summary, what you want to take away from this is that the only thing that a spectroscope really does, it takes starlight in and your raw spectra comes out. And whether it's your eye that's looking at the raw spectra at this end, or whether it's a camera, it all works the same as far as the light going through the system. Okay, so the Fort Wayne spectroscope in schematic form is this. We have three sets of components. We have the observing telescope, we have the spectroscope itself, and then a data acquisition and guidance PC. That's the equipment that I mentioned that was in the control room. The telescope itself is the 16-inch. It's a Ritchie criterion type telescope. It has a finder scope that we have a camera in, so that we can use that for either guiding or finding very dim objects. Turns out to be very handy to have a very sensitive camera that can see objects that are a lot dimmer than what your eye can see. So we have an easier time finding dim stars or galaxies, what have you, that we want to point the spectrograph at. The 16-inch telescope, pardon me, sits on an automated mount, this RCX 400. It can take commands from a computer that allows the telescope to be controlled to either track a star better than what the mount can normally do, or it can be commanded to go to a new object from the computer. And it also provides some compensation for mechanical defects and things like the gearing on that allow the telescope to track more accurately. The next piece is the spectroscope itself. It's called an LHIRES. That's an acronym. I won't go into what the details of that are, but it has to do with the configuration of the internal, the optical path. It has two cameras that go into the spectroscope. It has what I call a slit camera. It's normally used for guiding as well as positioning a star on the slit. I mentioned the slit just a moment ago. It provides us that collimated light source. And it has the sensor camera, which is where the raw spectra is viewed. And since it's a digital camera, it just takes a picture of it, sends it back to our data acquisition and guiding PC. These are USB peripherals, and so we have to have a hub, for all that to be gathered together. We have a number of major pieces of software to run this thing. The guiding is done by an application called PhD, and it has a subsystem called ASCOM. We do our camera control with a package called SharpCap. Not only does it do camera control, it allows us to do focusing, precise focusing, and it also is involved in setting up the polar alignment so that we have as little tracking error as possible based on a very accurate polar alignment. There's also a package called AVIS, which allows us to look at the images that are taken off of the spectroscope. We can do some editing with that, but mainly viewing to make sure that we have the right exposure. It tells you what the pixel values are, so you can see how deep your exposure is. We have two analysis packages right now called VSpec, Visual Spec, and Real-Time Spec, VSpec and RSpec. We have a package on the PC called Stellarium, and it's a planetarium software package. And its very attractive feature is that it holds a database of over 600,000 objects. The telescope itself has only about, I think it's about 200,000 objects. So one of these days, we're going to get Stellarium integrated into the control loop here, and so we'll be able to use Stellarium to command the telescope to move to a new object. That'll be very handy when it's cold out again, and so we won't have to go out on the floor in order to use the hand controller. But that'll be available later this year. The EQ mod package and the plate solver package, they provide functions that aren't really critical to our operation right now, and so we'll get to those hopefully later in the year, but they're not critical at this point. So visually, this is what it looks like. Mentioned the 16-inch RCX 400. That's what you see here. The spectroscope itself hangs off the back of it, and the light path is through this part of it right here. So the spectroscope takes the place of the eyepiece. The spectroscope, as I mentioned in the previous slide, has two cameras: the slit camera and the sensor camera. And it also has this very important piece, the micrometer. This allows us to change the viewing angle, or changes the angle of the diffraction grating, so that we can scan across the full range of light that's available from a star. The data acquisition and guide PCs are just, your office kind of a PC. It's nice to have the 2 large monitors so that we can support the 3 cameras and easily see what's going on. Excuse me. So capabilities that we currently have involve the hardware, the telescope. We can look at the entire visual wavelengths from 3,700 to 9,000 angstroms. So that's near ultraviolet to near infrared. We can vary the resolution of the spectroscope with the different grading packages that we've got. We've got 4 of them, and 300, 1200, 300, 600, 1200, and 2400 lines per millimeter. So the gratings themselves are like mirrors that have lines cut into them. And so when I talk about the lines per millimeter, that means exactly that. They have up to 2400 lines per millimeter across the face of the grating. So it provides us quite a few resolution options there. So it's really a very flexible spectroscope. We do have auto-guiding capability, and the auto-guiding capability has just been available since late December, early January. We're just starting to kind of learn how that works and see what needs to be done in order to actually hold the star on the slit. The slit itself is very small. It's 23 micrometers. So that's 0.0023 millimeters. Very small slit. So not a whole lot of light comes through it, and you have to precisely track in order to keep the star on that slit. I mentioned the AVIS product. It's the software package that does the spectral editing and derotation. We can crop it. We can do some other things with it. So it's a very handy feature. If you don't have the data camera in at precisely the right angle, you have to derotate it, and so that's the package that does that. The type of analysis that we can do with VSpec or RSpec is to create blind spectra from the raw spectral images. We can do the various calibrations that are needed with that, which the 2 primary ones are the wavelength calibration and intensity. And we'll look at a couple slides related to that so that you can see what that is. And you can combine these. Since the camera has a limited viewing range, we have to break up the spectra into a number of bands. And then if you want to have the entire spectra through the visual range, we have to recombine those into a composite line spectra, and you'll see an example of that as well. Both packages come with a line library, and so when you show it what wavelength you're interested in, it will tell you what element creates that particular line. So you can actually identify the components, the chemical element components that make up a particular star or a nebula. We'll be able to do redshift measurements with that same measurement capability. Also rotational velocity, like of Jupiter or Venus or Mars, we'll be able to handle. And then perhaps later on, we'll be able to actually investigate the magnetic properties of the stars. There are other capabilities within these analysis packages, but you really have to get to know them quite well. And right now, we're just starting to explore them in some depth. So this is a more detailed investigation or a description of what goes on inside the spectroscope. And you can see the light path as it goes through the spectroscope. So light comes in the top. The slit is really hard to see, but it's right here. So the light goes through the slit. There's a mirror right here that takes it through the collimating lens. It hits the diffraction grating, which breaks it up into the rainbow. That rainbow of colors is transmitted back through what was the collimating lens, but is now the viewing lens, and sends it out to the to the focal plane where your camera's image sensor is supposed to be sitting. And we changed the angle that the diffraction grating is sitting with that micrometer, and you can see that right here. The slit camera, which is used for guiding, gets its information from all the light that doesn't go through the slit. The slit plate itself is highly polished and acts as a mirror, and so that light path goes up to another mirror and then comes out through the to the guide camera, slit camera that you've got right here. This also has a calibrating bulb in it. So we have a neon bulb in there, and a neon bulb puts out a lot of lines of well-known wavelength. So you can use that to calibrate any of the spectra that you take with this spectroscope. Again, the thing to remember about the spectroscope is starlight goes in and your raw spectra comes out. So, but this is the light path. This is the way it basically works. So the process of taking a raw spectral image and producing something that you can deal with is illustrated in the next in the next few slides. So starting at the top, this is the raw image of Betelgeuse in one of the middle wavelengths. So we see the raw spectra at the top, and the raw spectra, really the size of it reflects the width of the slit. It was kind of a shock to me to see such a very small spectra compared to the neon spectra that you have here. The neon spectra fills the entire slit width, and so you get these very long lines. But you do so. The first thing you do is obviously you take the spectra of the star that you're interested in. The next thing you do is you take an image of your neon bulb, and then the step after that is to run it through your analysis package to go from these raw images to your line spectras. And so the spectra that we have down in this third image right here is the line spectra from the neon. And these neon lines, as I said, their wavelength is very well known. And so you can assign each of these lines a wavelength. And then in the analysis package, allows you with these identified wavelength, line wavelengths, it creates what's called a dispersion equation. And the dispersion equation transforms these pixel numbers. These pixel numbers are just the row numbers coming out of the camera. So each camera has a series of rows and columns. The columns are indicating the intensity, and each of these pixels in each of the rows should be changed to a wavelength. We're not really interested in what pixel number this particular indentation or this particular line is related to. We're interested in its wavelength. And this dispersion equation allows the program to change the pixel number to a wavelength. And the numbers that are up here on the calibration spectra right here, these are the angstrom wavelength numbers for each of these lines. So 4,700 wavelengths to over 5,700 angstroms is what we have in here. So it's about 1,000. So after you get your wavelength calibration, that's the one that you absolutely have to have in order to do any more work on this. In order to identify elements, you need to have the wavelength identified for each of these. And each of these indentations here are the absorption lines. And so each one of these represents, not by itself, but in groups, they represent a particular element. And by putting the cursor on this, it'll tell you what line what element created this line. The other thing that you'll do next is an intensity calibration. If you want to know the star's temperature, or its magnitude, you have to have an intensity calibration so that you can make that measure. We'll take a look at that next. Well, not right next, but there is another step. There's always another step. The next step is actually to compensate your intensity readings, and there's a number of factors that come into this. We need to remove the distortions created by the camera itself, by the telescope, and by the sky. So the camera's contribution to these distortions has to do with its sensitivity at each of the wavelengths that we're looking at. Most cameras don't really see into the deep blue very well, and so their sensitivity is low when you get to the left side of this graph. This is the ultraviolet end, and they peak in the green area, which is in here, and then they roll off as you get into the red and into the infrared. So part of this instrument response curve is intended to compensate for that change in camera sensitivity. Also, the coatings that are put on telescopes can absorb light in the UV and the IR regions. They let the center part of the visual range pass. And then the atmosphere itself can disperse either red or blue light. And so you want to be able to take account of that as well. And it would seem like a really complicated thing to do, but it turns out in the digital world, it's a point-by-point division with the values in the divisor, right? Yes, in the divisor coming from this curve, and so you take the number off of this curve and you divide it into the number that comes from this part of the curve, and you get a compensated value for it. And you can see the effect that it has. This is the raw curve. This is the compensated curve, and you can see that where it's low here, this curve actually brought it up quite nicely, and you get this. You get a true picture of what the overall spectra of Capella looks like, and that will allow you to calculate temperature either by finding the peak of this curve right here. You find the wavelength of the peak, and you can use that to calculate temperature, or you can use the level of the continuum using something called Planck's law. The other thing that you do with this is to identify elements, and I don't know how well you can see this. It's not very clear on my screen, and I'm fairly close to it. But each one of these major lines you can identify, as I've mentioned a couple times now, looking for something particularly clear. We have some lanthanum, I think, right here, and iron. There's lots of iron in most of the stars. Capella is no exception. We have the magnesium triple down here in this region, and this is a region to keep in mind. We're going to look at that on a couple of other objects a little bit later. There should be some hydrogen floating around here. Here's a hydrogen delta. We've got you've got K line right here. We've got the G line right here, which is a molecule, the CH molecule. We got a hydrogen, another hydrogen absorption line here. We should have another hydrogen beta right here. So just by having this library of elements available, you can identify quite a few of the components of the star that you're looking at. So that's chemical identification. And again, looking at the composite spectra, we've got the hydrogen beta, the D line, and hydrogen alpha. And this telluric oxygen and H2O, it turns out these actually come from our atmosphere. So the atmosphere at this wavelength is our atmosphere. The atmosphere of the Earth is absorbing light from this star, creating this characteristic curve right here. So I mentioned measuring the temperature by the maximum wavelength, and you can take either one of these. They're really close in intensity, but as I recall, this one is the closer of the two. I probably don't have a very good instrument response curve, so this should be up a bit higher. And it supports a value of 4,970 kelvins. So this composite was made of all of the previous pages spectral wave bands, and the analysis program put them all together. Just another set of spectra from the star Vega. And I think I won't spend a whole lot of time here. More hydrogen. This is a very strong hydrogen line. You can tell it's strong because it's a large gap and it's wide. And here's the composite of Vega with the major hydrogen lines identified. There's a library of these composites. This one's the Pickles library. And as you can see, the shape of my Vega and their Vega are really pretty close, and the hydrogen lines show up all in the right place. The other thing you can do is actually do classifications of the stars. There's about 7. There's 7? Is there more than 7? Let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 8 or 9 classifications of stars. The classifications are basically just the range of temperatures, and they indicate where they're at in their stellar life, in their evolution. And the major classes are identified here, just shown for reference. These I've got 3 or 4 of mine in here, and the rest come from those models, the library stars that we saw in the previous slide. So the O-class stars are the hottest temperature stars, and these M-class stars are the coolest at around 3,500 kelvins. You start to see molecules, all kinds of molecules like water, show up in the cooler stars. So I mentioned the hydrogen triplet earlier. This is a piece of the sun spectra that was taken with our spectroscope in July of last year. And you can clearly see the triplet right here. Very nice raw spectra here. Jupiter also is sporting the same triplet. Very nice sharp spectral lines here. Now the sun is about 6,000 kelvins or so. And it has this. Here's the Capella spectra again. You can see a fairly strong magnesium triplet here as well. And then you can see Vega has a very weak triplet right here. So Vega's a much higher temperature star than the sun. So it doesn't seem like it supports the magnesium triplet just because of its temperature, but you still can see it. So the question that's being answered here is what light does Jupiter reflect? I mean, we know that Jupiter doesn't have a temperature of 6,000 degrees Kelvin, so it has to be reflecting light. And my guess, since the sun is closer, it would be reflecting the sunlight because it's closer. Anyway, you see the same kind of magnesium triplet from Capella, but it's too far away. So I think it has to be the sun. Anyway, these few slides demonstrate the capabilities that I'd mentioned earlier. We can create line spectra. We can do wavelength and intensity calibrations. We can combine spectra into composites. We have a line library to identify the elements. We can calculate star temperatures through 2 formats here, through 2 laws, the Vine law and the Planck. And eventually we'll be able to do these redshifts and rotational velocities. So that's what we can do now. And if you have a great deal of interest, you can get involved in the project yourself and explore some of the ideas that you might have for for projects or just for learning about the what stars and other objects in space are made from. So that's the overview, and take questions if there are any. Well, thank you.
Well done, Joe. Well done.
So, there you go.
A lot of hard work there.
Hey, Joe,
Yes, yes, Jim.
are you have any ideas of taking a spectra of I don't know, like a double star or something that's rotating to say, hey, that's pretty cool. You could see obviously the rotation of one star around the other. You know, it's something that might even appeal to, you know, maybe, you know, a physics person from high school like PJ, you know, would be kind of cool, you know. Yeah.
Well, yeah, eventually. We're really getting basic technique down right now. The status of the whole project is we're just working through the complexities of auto guiding. It'd have to be a
Yeah.
bright star, and we can do bright stars even without guiding. We just have to make sure that our position, our polar alignment is in good shape. So it's coming. It's coming. The ability to do that requires a little bit more work in auto guiding and in the analysis tools, so that we can separate the red shifts, the Doppler shifts, and that's what we would be looking for. With this tool, we have the capability of measuring the rotational rate of Jupiter and Venus, probably Mars too. Just measuring the shifts on the two limbs. So that's possible. We'll be able to do that.
Okay.
Of interest to me is the change in spectral types when of a variable, for example, a variable star like Delta Cephas, actually like Betelgeuse as well. As they change temperature, they change their spectral types, their spectral class. And I'd be interested in seeing that myself. That's one of the projects I'd like to do with this spectroscope, is to actually investigate what that looks like over time. And Ben and I have talked just a little bit about actually putting a monitoring program together for Betelgeuse. If you remember, about was it a year ago, a little more than a year ago, when Betelgeuse dimmed considerably, and there was even talk about perhaps it was going to go supernova.
Yeah.
And it would have been kind of nice to be able to point to data that we'd already taken to follow the progression of the changes in Betelgeuse that occurred before it became so dim. But maybe the scientific community overreacted on that, because Betelgeuse is a known variable and has gone into fairly deep cycles in the past. So maybe there was just a bit of hype in that, but still.
I think the hype was that it's never been that dim before. Like, it basically disappeared for a while. I think that was where the hype came from.
It was definitely not the brightest star. It definitely was not the alpha star in Orion. That's for sure.
Yes. Yeah.
Hey, Joe, how did you come up with that instrument response so you could calibrate it out?
Well, there's a number of ways to do that, and the short answer is there's always a good video on YouTube for that, but it always involves a star, and whether the star is a star that you that's live, the one that you take in the sky when you're doing your other spectral work, or you take it out of the library. Now, the right way, the scientific way, is to take a star that's fairly close to it as you're taking your other spectrum, because then you truly get the contributions by the changes in the atmosphere. You can't get that from a static library star. But in order to take out at least the camera elements, I used a library star and then went through the process of, it's a 4 or 5 step process to create the instrument response curve. It's not real hard, but it's a little bit more than I'm willing to discuss at this point, because it involves smoothing, and there's division steps in there, and then more smoothing, and then you take it back and reapply it. to the star that you're.
Little
trying to get the,
tedious, huh?
It's what?
Tedious?
Tedious, yes, yes.
Okay.
But this other spectral group that I'm involved in, one of the things that they were talking about 2 weeks ago was putting together instrument response curves. And they were talking about atmospheric density numbers. You know, you want the star that you're measuring and the star that you're using as a reference to have the same density numbers. There are all kinds of complications that go into it. Create a science project just out of that.
So would you have to do that every time, or can you reuse that?
The scientific answer is every time. If you want science data, you have to do it every time because the atmosphere is,
Different.
as you know, as anyone that looks
Yeah.
through a telescope knows, the atmosphere is not static.
Right.
And so it would matter whether you were pointing closer to the horizon or closer to zenith. And so it changes a lot. So the answer is, yeah, with every observation, you should be shooting a reference star.
Hmm.
It's a little bit easier than the neon calibrations that you take every single time you change the angle of the diffraction gradient. So it's not quite that bad. And it is a mechanical process,
Yeah.
just like calibration.
So it's additional data you got to take and then and work on it.
Right. That's down the road. I'm not quite ready to do that yet. We don't have our technique down quite that tight yet,
Mhm.
but it is out there and people do it.
Okay.
I know 16 or 17 of them that do it, as a matter of fact.
Hmm.
I was on a 2-hour call with them today,
Hmm.
trying to get some hints and improvements in our technique.
It's not something that necessarily can be automated or anything. It's
Oh,
so,
I'm sure it is.
okay. So it can be automated. It's not something that's subjective, I guess. Yes and
The
no.
way I do it. I'm not sure how the professionals do it.
Yeah.
Everything that they can do by an automated process is done with an automated process.
Okay.
Ben would know more about that than me.
Hmm.
Every, yeah, you definitely want to automate what you can because that's a very tedious process. In my past life, it was actually a lot of simulations. So we'd actually put together very detailed computer modeling for our to account for the atmospheric effects. Now, I don't think we need to go anywhere, and I don't want to do it.
Yeah. Understand.
But yeah, I mean, I think I think taking reference to our data is it kind of depends on what we want to do with it. So, but if we want accurate data, the most accurate data possible, then yes, we want to take a reference star every time. But if we're just looking for lines, and at this point we're just kind of looking for lines and looking for, and if we just want to like look at redshifts of this particular object, we don't necessarily have to do it every time. But it's kind of but if we want to get the amplitude right, if we want to get the amplitude of the signal of the spectra coming out of it, then yeah, we're going to probably need to take a lot of reference star data.
Okay.
Yeah, a good flux density, good flux measurement.
Yeah.
All right. Another good program.
So we'll be out there. I'll be out there tomorrow night, trying to whip auto guiding into final form. They were insistent that we should be using slit guiding on the slit, which we haven't attempted yet. So another piece of PhD 2 that will have to be conquered. Too much flex between anything and the slit, so you want to guide on the slit.
Yeah.
So.
All right.
Yeah, and it's all accessible. I mean, it just takes a lot of reading, and if you're interested, you'll do the reading, and we have the equipment to provide the hands-on. So that's what it's here for.
Mm-hmm.
Yeah, I really appreciate your time on spending on this, Joe, and it's kind of neat to see you know, us go another direction in addition to photography and visual. It's pretty cool.
What do you
It is.
think, PJ?
I think it's generally neat. And it was also pretty interesting to learn how the spectroscope, is that the right word?
Yeah, it's a lot to bite and chew, isn't it?
It is.
Yes.
But so far, I think I'm handling it pretty well.
Yeah. Little pieces at a time.
It all turns out to be arithmetic at this point. I don't know of any advanced mathematics that we need in order to do the just to do the measurements, to do the temperatures, to do the line identifications. I don't even think flux, the intensity calibration is really not that mathematically intense. So there shouldn't be anything there that scares you away.